Hi, and welcome to our next session here in our ML Basics chapter in our lecture Introduction to Machine Learning. So this session here is, I don't know, I guess probably one of the most important ones in the first chapter. So this is on losses and risk minimization and empirical risk minimization. So I do want to, together with you, I want to do a first formalization, what we actually mean by learning, how we can mathematically specify that, what all of that means. I want to talk about the concept of loss functions, so functions that measure the difference between predictions and observed labels. I then want to define what we mean by the theoretical risk and the empirical risk. So these are two ways of associating, two very similar ways of associating a number with a candidate function from a hypothesis space, where that number tells us how much a certain candidate function matches our observed training data. And the difference between theoretical risk and empirical risk is that theoretical risk is the thing we are interested in, and it's computed with reference to the data generating distribution, and empirical risk is the stuff we can compute and we can work with. Yeah, and then we'll understand how that enables us to operationalize learning. And yeah, I guess this is why we call it, I don't know, machine learning, which I guess you could also say, I don't know, you could also say automatic learning, yeah, statistical learning, learning from data. I guess these later ways of defining the field might actually even be better terms than machine learning, because there's not so much machines involved, but rather mathematical concepts and algorithms. Yeah, and I guess data and statistics. So, in order for us to define what we mean by learning, the first thing that we should do is we should actually define what we mean with that and what the goal of that thing is, and we should talk about how do we evaluate models with respect to the observed training data. So maybe you've observed some data like that. Well, actually, some data like that, because we have a feature part and we have a target part. Maybe that's a regression problem. We looked at this before. So here we have some features like people in office, their salary, and then want to predict how many minutes per week they work. So I don't know how motivated they are or whatever. And there's some model that now transforms each feature vector into a scalar prediction, y hat. But of course, because it's training data and because it's supervised training data, we have observed some ground truth labels, which we can now compare with all of our predictions. And we now want to find a model from our hypothesis space that matches our training data best. In a certain sense that, I don't know, based on the features, reproduces the ground truth labels as closely, as good as possible. And that we now have to make mathematically precise. We have to specify what we mean by that, and I guess it's intuitively clear that it's likely a good idea and very helpful if we can compare a single prediction to a single ground truth label and then somehow measure the difference and measure the quality of that prediction. If we can do that for a single pair of target and prediction, we can do that for all of them, and that will help us to establish a function associated with a candidate model that, for the completeness of the training data, encodes how well our model reproduces our observed labels. But let's do this step by step. So the idea is now to come up with a function that simply compares these two guys here. And this concept, we will from now on call a loss function. A loss function is a bivariate function. I will use a capital L for it, L for loss, yeah. Bivariate because it takes two arguments. The first argument is going to be our observed label, so our y. And the second argument is going to be our predicted label or a predicted score. So for now here, for this session here, and for some some few sessions later on. Probably a bit easier and to do more helpful to focus a bit more on regression. So there's not really then a difference between different, I don't know, scale and how we encode things between label and output. So they live on the same scale. So label is going to be a real number and prediction is going to be a real number, and they should be as close together as possible. And we just want to measure difference between the two. Somehow there will be many examples and clarification later on for how we do this in classification. And it's going to be a little bit more difficult because there might be some scores, there might be probabilities, there might be hard labels and so on. And then we work with different loss functions. Let's forget about this for now. So let's focus a bit on regression. So a loss function maps from our true label space and from our score space, which in general might be R to the G, to a single number, and that's the loss. That's the error or the difference for this pair of ground truth label and predicted score. And here is a very simple but already useful example. So this is what we would call the absolute loss or the L1 loss. So what does this do? It simply computes the difference between y and f of x. I guess that seems reasonable. And then we don't really care about the sign. So we take the L and we take the absolute value, and this is why this is called absolute loss. And because there are these LP metrics in maths, we might call this the L1 loss for short. And here's a nice little picture how this might work if we would use some form of regression model. So maybe that's a simple linear model and maybe it just acts on one feature. So here we have our feature x, here we have our label y, and I don't know if we now look at the y-axis or the y-coordinate. Here we have our training data. If we look at the y-coordinates of these points, these are of course our ground truth labels. And for a specific point, maybe this guy here, this would be our prediction, or the y-coordinate here of this point would be our prediction of our linear model that I'm looking at here. And this might be my ground truth label. And what I'm simply now computing is the difference in y between these 2 points. So the length of this straight line between the 2 points. The difference in y coordinates. And this difference is sometimes also called a residual. Okay, so some people call it like that. And you can also see here how this residual is mapped by the loss function to the loss value. So you get these two different shapes here of the L1 loss and the L2 loss. Okay, how can we now extend this measurement, this point-wise measurement of an error to a measurement, to a quality measurement of our complete function f, of our model f? And we will do this by now establishing the so-called theoretical risk. So the theoretical risk of a candidate model by simply saying, well, this is the expected loss of our model when we simply integrate out over our underlying data generating distribution. So you can either write this simply as an expectation of the loss L when you plug in the random variable x, y, sampled here, taken from, generated by our underlying distribution capital P, or you can just simply write out what the definition of the expected value is via this integral form here. And the simple meaning of that is that we now encode the average error that we incur when we use f on data spawned by, generated from capital P. And the whole idea of learning now is find a hypothesis that minimizes this, okay? Because that is, in a hopefully reasonable, intuitive sense, the model from our hypothesis space that predicts our output best with minimal error if we measure that error A over the data generating process, so our underlying distribution that our data comes from, and B, with the loss function of our liking, C, minimized over the hypothesis space that we picked. Now, are we now done? Well, no. First of all, we practically have to somehow minimize that now. That might be challenging in general, even if we know capital P, but unfortunately it's worse, we don't. So this distributional, this data generating process here, this distribution on x, y, this is usually assumed to be unknown, right? So we just have some data from it, but we don't know how this looks like. And we might not even be willing to assume that we know the functional form of that. So we could assume that this is somehow, I don't know, normally distributed. Even that might not work if, just for very formal reasons, if, I don't know, x is some numerical feature vector and then y is discrete and so on. Even that simple thing might not, then this simple assumption might not work, but maybe x is numerical, maybe y is numerical. Yeah, I guess we could assume that they are all jointly Gaussian, but this, we might consider this a very, I don't know, a too constraining, a too restrictive, too severe assumption. Some ML models actually do that. So, I don't know, things like discriminant analysis and so on make these assumptions, and we could do that. But usually we don't. Now, maybe we can, or maybe I should have started a bit differently. I guess if capital P is unknown, one reasonable approach could be maybe we can estimate it. And in order to estimate capital P, we do have to make some assumptions about it. Either we assume some we place some very strict assumptions on capital P regarding its form. I don't know, something like a normal distribution or whatever. And then we should be able to estimate P in not super high dimensional spaces, maybe. Or we could even do non-parametric density estimation. Maybe we could do something like kernel density estimation. That usually doesn't scale too well to higher dimensions. And in general, if we study this a bit more, we'll also figure out that this whole problem of density estimation here might actually be harder than directly estimating F. Yeah? Because in a certain sense, we have now to learn more from the data. We have to learn something that's more complex. And this learning problem is quite hard. I'm not saying that this is impossible. We cannot do that. But it might actually require more data, might be more complicated than directly thinking about, can I not maybe estimate F directly? And just estimate F and not this complete density and then constructing F from that. So how about we try that? And how about we think a little bit about what we have and what we can do with that? Because what we have is an IID sample of n data points from our underlying distribution capital P. And this might obviously help us to approximate this expected risk empirically. So what we will do is this very, very old trick of simply, let me actually remove some of my scribbling here so the slide becomes a little bit cleaner. I'll just substitute my theoretical expectation here, or this integral, by a finite, concrete, empirical sum. So, and I've done this here. Yeah? So I'm just going to sum up all of my losses, all of my individual losses over the training data. Yeah? So either you can say, well, this makes intuitive sense to me anyhow, so I want to measure my prediction error, all of the feature vector, comma, ground truth label points I have observed, and want to find the function for which this error is minimal. Or you're saying, well, it also makes sense to me mathematically because I'm just substituting this expectation by a finite sum over my IID samples. And so this thing here, I will now call R as well, but I'll call it Remp for empirical risk. Okay? And this is a function, I guess you could say operator if you want to. It's a function that takes an F, which is also a function, that's a model, computes this summed loss over all of the training data, and then outputs some summed loss, yeah, which indicates how close our model predicts our training data. Okay? So this associates one's quality score with each element in our hypothesis space, or at least we can do that. Okay? And this score should encode how well does F fit the training data. This actually now brings us very, very close to optimizing over our hypothesis space to figure out what the best fitting model is and to really now operationalize what we mean by learning. So for now, it is this mapping here, from the hypothesis space to this empirical risk score. So I guess we can also look at these examples here below. So again, it's a univariate super simple toy regression example. So we have one x here with our y. We can look at the data. We can look at this candidate function here. And I'm not really fitting it here to the data. I'm just like trying it out. Yeah? So I'm not there yet that I can learn the optimal parameters. I'm just using one arbitrary model from my hypothesis space. I'm just like plugging it into this plot. And then for each point, I'm measuring the loss. Maybe this, not really maybe, but using this L1 loss, this absolute loss before. So for each residual, for each point, and we compute this absolute value, and then we sum all of them up. And what we can see here is that this gets you an empirical risk score of approximately 58 points. And here's a different model, a different slope, different intercept, and we do exactly the same thing. And I can now compute the empirical risk of that model as well, and that's approximately 96 points. So apparently this model here is worse. This is not as good as this guy here on the left-hand side. So that's a better model, apparently, according to that loss function from that hypothesis space that we have picked. Now, we can compare models. Yeah, maybe we can now get a little bit closer to optimizing them automatically. Few little details before we do that. So of course we could also, it's a very basic comment, we could also define something like an average loss, usually calling that R bar, because bar is a standard symbol for averaging in statistics, and that just divides everything by n, so I get an average loss per observation. Yeah. Might be quite nice for interpretation. In terms of optimization, this constant factor of 1 divided by n doesn't really make any difference at all. I usually just use the simpler summed up loss here, and I really don't want to talk about this. So for now, for us here, these two things really don't make a difference. Sometimes later on they do, but yeah, I'll make that clear in notation, and the context will make clear what I'm using. Usually for now I'm using this summed loss without the bar. Which is a little bit more interesting for us now is that usually we don't really want to act on f because f is a function and functions are complicated. But we've already agreed upon that our functions are characterized, specified, identified by some d-dimensional parameter vector theta. So I could also simply write my empirical risk as a mapping from my parameter vector, because each parameter vector uniquely identifies a candidate function, a candidate model, to the empirical risk score. So instead of me plugging a function f now into the empirical risk function, I just plug in a parameter vector, and it should be clear that I can calculate the thing in exactly the same manner, and it's just a very, very minor way of rewriting things. But this will help us now a lot because, well, parameter vectors are, as the name says, vectors, and on vectors we can nicely compute and we can optimize on them. Yeah? Bit easier than directly operating on some arbitrary function. So what can we now do? So maybe we just like generalize this example here a little bit. So how about we look at different, not two, but multiple different linear functions for this data. And I'm pretty sure for this slide I exactly continued working on this example. So if our hypothesis space would be finite, so there would be a finite combination of intercepts and slopes. Of course there is not, okay? Assume there is. So there would only be 4 models in our hypothesis space with these 4 intercept slope combinations. Of course I could now exhaustively tabulate all of them. I could, for each model, I don't know, if I want to program this in a simple for loop, maybe you even want to try this out as a little, I don't know, exercise. So actually, being serious here, that would, yeah, probably helpful for a beginner. Simulate some data like that, yeah, try out a couple of, I don't know, maybe linear models, compute the empirical risk with a loss function of your choice. You can tabulate things, and you can look at these 4 different functions here, and you can look at their associated empirical risk. You can just take the one that's best. And apparently that is exactly the example here that I looked at here. So that had, what was that? Was an intercept of, was a slope of 1.5 and an intercept of 1. Yeah, looks approximately correct. So it's pretty sure it's exactly this function here. And in this table, I tried out 3 different other slope and intercept combinations, and they're working less well. Unfortunately, even this space here, even this very simple space, and this is pretty much true for any machine learning model we're interested in, is infinitely large, right? So there's an infinite number of intercept terms we could choose, and there's an infinite number of slope terms we could use, and we now have to choose a combination, and even just R as a real line is uncountably large. So we can't exhaustively write down all of these models in a simple for loop and then just somehow, I don't know, pick the best of these. So you have to do something else. But this other thing that we're going to do is we're just going to simply see, hopefully we have seen this before, is that the empirical risk is, well, it's a function. Yeah, it's a function that maps a parameter vector to risk. So that function gives us such an error surface here, but that's not a new concept. That's just me visualizing that function, okay? So it's this mapping from the parameter vector theta to the associated risk value, and I'm just visualizing that here because I guess that is helpful for what comes now. And I can plug in my 4 arbitrary points that I just tabulated before, and you can see, okay, these points, they lie somewhere here on this error surface. But yeah, why should they lie in the best value of this error surface? And what is actually that best value? That best value is located somewhere here, I hope. Not great of identifying the perfect spot on this 3D plot. So the whole idea now is to just write down this function here and say, well, if I want to find the best parameter vector because I want to find the model, a candidate model that reproduces through predictions my labels with with an error as small as possible. So I guess that's the minimization problem. It's a minimization problem over on my parameter space, over the parameter space of my hypothesis space. So I find the optimal parameter vector, so this empirical risk here becomes as small as possible, okay? And I'm now just going to say that we're going to do exactly that. Yeah. So this might be our first formula that could encode what the core of machine learning is. Yes, I'm a little bit reluctant of stating it like that because we're not finished with this, and I guess the field is a little bit too large to just simply pin it down through a simple formula, but this is a very important one. Yeah, and we'll call that, the principle behind that we'll call empirical risk minimization, because we're minimizing the empirical risk to operationalize what we mean by learning. And the result of that minimization I'm going to call theta hat. And I guess if I want to be super formal and correct, and I guess that's usually a good thing, so I should probably say theta hat is an element of this argmin here, because this optimal parameter vector might not be uniquely identifiable, and there might be multiple ones of the same quality. So more importantly, how do we solve this problem? Well, practically, we usually do this by some form of numerical optimization. I'm going to talk a little bit about this in an upcoming session. This lecture is not going to focus on this too much. For us now, what this means is that we have this error surface here, and we somehow, through some efficient numerical optimizer, walk down this error surface to the minimum, maybe the global one, hopefully the global one. And we have now, in a certain sense, specified what we mean by automatic learning from data, and we have reduced this problem to numerical parameter optimization over a parameterized function space. And that now gives us a very practical, clear handle on how to implement, how to perform, how to maybe also mathematically study this problem of automatic learning from data, of statistical learning from data. And that this reduction to numerical parameter optimization is, well, just part of the story and is not the complete picture. Well, it's helpful for now. It's going to be helpful later on as well. It's an important part of the story, but it's not everything. And I don't have time to explain this now, but many other sessions will shed different, I don't know, spots of light on this more, and it will enlighten you hopefully more. Maybe I can say one thing for now, and this is, it is super useful and reasonable and good to encode this problem of learning through this empirical risk minimization here. But maybe let's talk about two problems. So one problem could be if we have a very low amount of data and we have a very flexible family of functions available to us, we might overfit. So we might, through aggressive optimization, we might identify a function that models our training data very well, but that doesn't generalize very well to new data. This will be a very important topic later on in the lecture and everything, I guess, that comes next. And one reason for that is we really are interested in minimizing this thing here, so the theoretical risk, but we are working on this approximation here. Yeah, and depending on how small our training data is, and depending on how complex and rich our class of considered functions is, so our hypothesis space, we might be more or less happy about the gap between the two. And overfitting is a problem associated with this gap between the two things, and that we are not really working on the stuff we are primarily interested in, but the next best thing. And that this introduces a couple of problems that we have to deal with later. The other thing is we might not only be interested in minimizing this, but we might also be interested in things like inference and understanding and so on. And then it's also not only about aggressive optimization in order to reduce prediction error. I guess I'm already going into full mode of covering different other topics and chapters here in the lecture, so I don't want to do this. I will stop here. I hope you enjoyed this. See you in the next session.